A joule is a unit of energy, and power is the rate at which energy is transferred or transformed. So, a joule per second is the rate at which energy is being transferred or transformed. 1 horsepower is equal to 44,760 joules per second. This means that a 1 horsepower engine can transfer or transform 44,760 joules of energy every second. Here are some examples of how joules can be used to measure the rate of dissipation of power per unit of time. Firstly, a 100-watt light bulb dissipates 100 joules of energy per second. Secondly, a 1 horsepower engine dissipates 44,760 joules of energy per second. Thirdly, a car engine that is running at 3,000 revolutions per minute is dissipating approximately 100,000 joules of energy per second. Joules can also be used to measure the amount of energy that is stored in an object. For example, a 1 kilogram mass that is moving at a speed of 1 meter per second has a kinetic energy of 0.5 joules. Joules are a versatile unit of measure that can be used to describe a wide range of physical phenomena. They are especially useful for measuring the rate of dissipation of power per unit of time. Thinking about electrical circuits, voltage represents electrical potential energy measured in volts. Current measured in amps represents the flow of electrical charge. The power, measured in watts, is the rate at which electrical energy is transferred or consumed. A joule, in this context, is the amount of energy transferred or consumed when 1 watt of power is applied for 1 second. So 1 watt is equal to 1 joule per second. Imagine a simple circuit with a resistor connected to a battery. The battery provides the electrical potential energy or voltage, causing current to flow through the resistor. As the current flows through the resistor, electrical energy is converted into heat energy. The rate at which this energy is converted into heat is the power dissipated by the resistor, measured in watts. If you know the power in watts, you can determine the amount of energy dissipated in joules over a specific time period. For instance, if a resistor dissipates 10 watts of power for 5 seconds, the total energy dissipated would be 50 joules. To calculate the power dissipated by a resistor, you can use the formula power equals current squared times resistance, or power equals voltage squared divided by resistance. Knowing the voltage and current, or the voltage and resistance, or the current and resistance allows you to determine the power in watts, and from there, calculate the energy dissipated in joules. Consider a heating element in an electric stove. The heating element has a resistance, and when connected to a 240-volt power source, a certain amount of current flows through it. The power dissipated by the heating element is what causes it to heat up. If the heating element dissipates 1,000 watts of power, it means it is converting 1,000 joules of electrical energy into heat energy every second. Understanding the relationship between joules, watts, volts, and amps is crucial for analyzing and designing electrical circuits and systems. It allows engineers and technicians to determine the energy consumption, heat dissipation, and overall performance of various electrical devices. Furthermore, understanding joules allows one to analyze energy usage in the context of the National Electrical Code, or NEC. The NEC provides guidelines and regulations for safe and efficient electrical installations. Many NEC articles and tables refer to power and energy calculations to ensure that electrical systems are properly sized and protected. For example, when determining the appropriate size of conductors for a circuit, the NEC requires calculating the total load in amps. This load is directly related to the power consumed by the devices connected to the circuit. By understanding the power consumption in watts or kilowatts, which can then be converted to joules per second, electrical professionals can select the correct wire gauge to prevent overheating and ensure safe operation. Similarly, when selecting overcurrent protection devices such as circuit breakers or fuses, the NEC mandates that these devices be rated to protect the circuit from overloads and short circuits. The rating of these devices is based on the current carrying capacity of the conductors and the power consumption of the connected loads. Again, understanding the relationship between power, energy, and current is essential for selecting the appropriate overcurrent protection devices. In addition, the NEC addresses energy efficiency in various sections. It provides guidelines for selecting energy-efficient lighting, motors, and other electrical equipment. By understanding the energy consumption of different devices in joules or kilowatt-hours, users can make informed decisions about which equipment to use to minimize energy waste and reduce electricity bills. The NEC also covers the installation of renewable energy systems such as solar, photovoltaic, or PV systems. These systems generate electrical power from sunlight. The amount of energy generated by a PV system is typically measured in kilowatt-hours, which can then be converted to joules. Understanding the energy production of a PV system is crucial for determining the size and configuration of the system, as well as for calculating the potential energy savings. In summary, joules represent a fundamental unit of energy, and understanding the relationship to power, voltage, current, and other electrical parameters is essential for various electrical applications. The NEC relies heavily on these concepts to ensure safe and efficient electrical installations, covering aspects such as conductor sizing, overcurrent protection, and energy efficiency. To elaborate further, consider a scenario involving electric vehicle charging. Electric vehicles store energy in batteries, and the capacity of these batteries is often measured in kilowatt-hours. 1 kilowatt-hour is equal to 3.6 million joules. When an electric vehicle is plugged into a charging station, electrical energy flows from the charging station to the vehicle's battery, increasing the battery's state of charge. The rate at which energy is transferred is the charging power, typically measured in kilowatts. A higher charging power means that the battery will charge faster. For example, a level 2 charging station might provide 7.2 kilowatts of power. This means that it is transferring 7,200 joules of energy to the vehicle's battery every second. The amount of time it takes to fully charge the battery depends on the battery's capacity and the charging power. If the battery has a capacity of 60 kilowatt-hours and the charging station provides 7.2 kilowatts, it would take approximately 8.3 hours to fully charge the battery. In this scenario, understanding joules and kilowatt-hours is crucial for determining the charging time and energy consumption of the electric vehicle. It also helps in planning the electrical infrastructure needed to support electric vehicle charging, including the sizing of conductors, overcurrent protection, and transformers. Furthermore, consider a data center that houses numerous servers and networking equipment. These devices consume a significant amount of electrical power, which is converted into heat. The data center must have adequate cooling systems to remove this heat and prevent the equipment from overheating. The amount of heat generated by the equipment is directly related to the power consumption in watts. If a server consumes 500 watts of power, it is generating 500 joules of heat energy every second. The cooling systems must be able to remove at least this amount of heat to maintain a stable operating temperature. Data centers often use sophisticated cooling technologies such as chilled water systems or air conditioning units. These systems consume additional electrical power, so it is important to optimize the cooling system to minimize energy consumption. By understanding the power consumption of the equipment and the efficiency of the cooling systems, data center operators can make informed decisions about how to manage energy usage and reduce operating costs. In these examples, joules serve as a fundamental unit for quantifying energy transfer, consumption, and dissipation. Whether it's calculating the energy stored in a battery, determining the charging time of an electric vehicle, or managing the heat generated in a data center, understanding joules and their relationship to other electrical parameters is essential for a wide range of applications. Moreover, the concept of joules extends beyond electrical systems and is applicable to various other fields of science and engineering. For instance, in mechanical engineering, joules are used to measure the kinetic energy of moving objects, the potential energy of objects at different heights, and the work done by forces acting on objects. In thermodynamics, joules are used to measure the heat energy transferred between systems, the internal energy of substances, and the enthalpy and entropy changes in chemical reactions. In chemistry, joules are used to measure the energy released or absorbed in chemical reactions, the bond energies of molecules, and the activation energies of reactions. These are all measured in joules, or related units like kilojoules. In physics, joules are used to measure the energy of photons, the energy of particles in atoms, and the energy of nuclear reactions. The versatility of joules as a unit of energy makes it a fundamental concept in science and engineering. By understanding the concept of joules and how they relate to other physical quantities, scientists and engineers can analyze and design systems and processes in a wide range of fields. Considering the context of sustainable energy, joules play a crucial role in assessing the efficiency and impact of different energy sources. For example, when evaluating solar panels, one key metric is the amount of electrical energy they can generate per unit area, typically measured in watts per square meter. This power output can then be converted to joules per second per square meter, providing a direct measure of the energy flux from the solar panel. This allows for comparison between different solar panel technologies and helps in determining the optimal placement and configuration of solar arrays. Similarly, when analyzing wind turbines, the energy they generate is determined by the wind speed and the size of the turbine blades. The kinetic energy of the wind, which can be calculated using joules, is converted into mechanical energy by the turbine blades and then into electrical energy by a generator. The efficiency of this energy conversion process is a key factor in determining the overall performance of the wind turbine. Understanding the joules of energy captured from the wind allows engineers to optimize the design of wind turbines and wind farms for maximum energy production. In the context of energy storage, joules are essential for quantifying the capacity and performance of batteries and other energy storage devices. A battery's energy capacity is typically measured in watt-hours or kilowatt-hours, which can be easily converted to joules. This indicates the total amount of energy that the battery can store and deliver. The rate at which the battery can deliver this energy is determined by its power output measured in watts. The relationship between energy capacity and power output is crucial for determining the suitability of a battery for different applications such as electric vehicles, portable electronics, or grid-scale energy storage. By understanding the joules of energy stored and delivered by a battery, engineers can design more efficient and effective energy storage systems. Furthermore, joules are important in evaluating the environmental impact of different energy sources. Fossil fuels such as coal, oil, and natural gas release greenhouse gases when burned, contributing to climate change. The amount of energy released per unit of fossil fuel is typically measured in joules, and the amount of greenhouse gases emitted per joule of energy is a key factor in assessing the environmental impact of these fuels. Renewable energy sources, such as solar, wind, and hydro, have a much lower carbon footprint than fossil fuels. By comparing the energy output and greenhouse gas emissions of different energy sources in terms of joules, policymakers and consumers can make informed decisions about which energy sources to use to minimize environmental impact. In summary, joules are a fundamental unit for quantifying energy in all its forms, and they play a crucial role in understanding and evaluating energy systems. From assessing the efficiency of solar panels and wind turbines to quantifying the capacity of batteries and evaluating the environmental impact of different energy sources, joules provide a common language for comparing and analyzing energy technologies. As the world transitions to a more sustainable energy future, understanding joules and their applications will become increasingly important. Also think about arc flash, a dangerous phenomenon in electrical systems. An arc flash is a type of electrical explosion that occurs when there is a fault in the electrical insulation or when a conductive object comes too close to a live electrical component. Arc flashes can generate intense heat, bright light, and pressure waves, causing serious injuries or even death. The energy released in an arc flash is typically measured in joules. The amount of energy released depends on the voltage, current, and duration of the arc. Higher voltages, currents, and longer durations result in more energy being released. The energy released in an arc flash can be extremely high, reaching tens of thousands or even hundreds of thousands of joules. This energy can cause severe burns, blindness, hearing loss, and other injuries. To protect workers from arc flash hazards, it is essential to perform arc flash risk assessments and implement appropriate safety measures. Arc flash risk assessments involve calculating the potential arc flash energy at different points in the electrical system. This calculation takes into account the voltage, current, and clearing time of the overcurrent protection devices. The results of the arc flash risk assessment are used to determine the appropriate personal protective equipment or PPE that workers must wear when working on or near energized electrical equipment. PPE includes flame-resistant clothing, gloves, face shields, and helmets. The level of protection required depends on the potential arc flash energy. In addition to PPE, other safety measures can be implemented to reduce the risk of arc flash. These measures include de-energizing equipment before working on it, using insulated tools, and maintaining safe working distances. Arc flash training is also essential for ensuring that workers are aware of the hazards and know how to protect themselves. The NEC addresses arc flash safety in several articles. NEC Article 110.16 requires that electrical equipment be marked with a warning label indicating the potential arc flash hazard. This label must include the voltage, available fault current, and clearing time of the overcurrent protection device. NEC Article 130 provides requirements for electrical safety-related work practices, including arc flash hazard assessments, PPE, and training. NEC Article 240.87 provides requirements for arc energy reduction, which involves reducing the clearing time of overcurrent protection devices to minimize the potential arc flash energy. By following the requirements of the NEC and implementing appropriate safety measures, the risk of arc flash injuries can be significantly reduced. Remember, electrical safety is paramount, and understanding the energy involved in electrical hazards, measured in joules, is crucial for protecting workers and preventing accidents.